simulation specialists here in the US. I'm here to talk about optimizing large heat sinks, largely focused on the idea of solve time. So what can I do with the mesh to make this solvable on a single computer? What can I do with analysis methods to make this more efficient to solve? This is more focused on meshing and methodology rather than just some of the optimization tools that are built in. This is more about meshing and methodology. All right, let's take a look here. So optimizing these larger heat sinks, and I said this was for meshing and methodology. I had initially run across this idea for people working with large HVAC systems and for electronic vehicles. I'm sure there's other reasons out there. That's where I kind of got this started. So I'm going to focus on the heat sink like you might typically see inside of a computer, so something boxy with long, thin fins. But as these grow in size, I would worry about solve time and solving that in a reasonable amount of time, but still following best practices. So I might try to take advantage of high aspect ratio elements. I've seen these on like the trailing edge of airfoils, for example, in CFD files. So I'll try to take advantage of them here. We can also try replacing the heatsink fins with porous media. This is a three-dimensional block representing the fins. I can use this and still achieve pressure drop and heat transfer with a far simpler CFD model. And then if it gets too big to solve on a local computer, I do have some methods with cloud computing that we could look into. With the techniques I'm talking about here, I'm largely working within these three types of tools that GoEngineer offers. One is SOLIDWORKS. So this is either typical SOLIDWORKS on your desktop or 3D Experience SOLIDWORKS using a 3D Experience add-in. I'm using SOLIDWORKS Flow Simulation for a lot of my CFD or 3D Experience Fluid Dynamics Engineer. They're really exchangeable. But cloud computing specifically is only available in the 3D Experience Fluid Dynamics Engineer role. All right. So how does a heat sink heat? So heat sinks largely work through conjugate heat transfer. Conduction is transferring thermal energy from the source through a bank of densely packed fins. The fins have a lot of surface area to remove thermal energy through convection. Radiation can come into play here. If the temperature difference is very significant, but in closed system and the temperatures that I'm talking about, largely I can ignore radiation. If I want to maximize the ability of the heatsink to exchange heat, I want to think about maximizing the surface area and the heat transfer coefficient. And I'm pulling these values from this equation. So the heat transfer coefficient is formulated with many different types of inputs, but the fluid properties is one big aspect of that. So, for example, changing the viscosity of the fluid could affect that heat transfer rate. Water with a higher viscosity will create higher heat transfer coefficients than air with a lower viscosity. I could also increase the velocity of the fluid flowing past the fins to increase that heat transfer coefficient. And then obviously to maximize area, I could do things like increase the number of fins, increase their height, their length, their width, to maximize that heat transfer. But I have to be careful. If I make the gaps between the fins too small, I'll reduce the velocity, which will reduce the heat transfer coefficient. So I got to be careful with what I do there. This is a quick example of me going through large gaps between the fins to very thin gaps. As I'm increasing that fin count here in the bottom row, I can see the effect on the temperature of the chip beneath it. So I can see that at a certain fin count, I have that lowest temperature. And then as I still try to increase that area, total area of all the fins, I'm affecting the velocity adversely and increasing the temperature again. So there is a sweet spot with how many fins I'd want to pack in there before I start affecting the velocity adversely. Now, that's a small case. Let's look at something a little larger that I can still solve on my computer. This is a very generic sample of what might be out there. The idea is that there are 25 battery cells. These are those green blocks with a lot of power being generated, 15 kilowatts. Right now I'm starting with 250 fins at the bottom, about 0.02 inches thick. Because of how much heat I need to reduce out of the system, I'm not going to just go with air. I'm going to use water to really help with that heat transfer coefficient. So there, around the fins, I've got water flowing past those fins. Around the battery cells themselves, there's just some stagnant air with initial standard temperature air. I'm going to use standard temperature and pressure for pretty much everything here. So starting with some average temperature water at atmospheric pressure, and arbitrarily chose 2.5 CFM, that's cubic feet per minute, as an inlet flow rate. Okay, that's the general setup. What might I want to do long-term with a design like this? Thing number one, based on where I did the inlet and outlet, which was just in the middle-ish of this assembly, the velocity is not very evenly distributed. I've got a lot of high-speed velocity right up down the center, but it's not evenly distributed across, this whole vertical section here, so it's not evenly flowing across each row of cells. So a first pass design iteration I'd be doing is, what can I do about the inlet and outlet to get that velocity more evenly distributed? How do I change my design? I would want to do this as quickly as possible, and I don't want to have to do a detailed analysis on every fin while I do that. But once I have that figured out, I would want to do a detailed analysis of every fin so that I can predict temperature accurately. I want to make sure that the temperature on those battery cells doesn't exceed a certain operating temperature. And then on top of that, I would want to optimize the length and the width and the height and how many fins am I doing to get that temperature as low as possible. So let's start with a baseline analysis. So you saw the setup there, and I'm going to start with a very coarse, basic default mesh. What does that mean? Take a look at these red cells here, these squares. That's my default coarse mesh that I'm doing. One of those cells crosses about 3.5 fins of the heatsink. That's these long black lines, these vertical lines. So one cell is crossing quite a few of them. That's not really accurate per se, but it can generally capture what's going on, and it's a good way to sanity check, is my setup working? So with just this type of coarse mesh on my computer, this took about 35 minutes to solve. I had a coworker help me out with this one. So they solved it on their computer, which was a little bit better than mine, a little bit faster. He also solved it on our services computer, one of our best machines. Got that down to about 9 minutes. So increasing the cores definitely reduced the solve time, which is nice. 9 minutes is not too bad. I feel like I could use that for some quick early iterations as I'm working on the inlet and outlet. But I did need a nice computer to make it that fast. Now, I did say this was coarse mesh, not necessarily fully accurate. Usually best practice is 2 to 3 mesh cells between each fin, between each channel here, to capture the velocity gradients, the pressure gradients along those channels, those gaps between the fins. But if I was to do something like this, I would likely end up with something between 10 to 100 million cells. That can be fairly long to solve on a single computer, too impossible to solve on a single computer. So I'm going to start veering towards this idea where I'm refining the mesh cells between the fins, but taking advantage of tricks to improve the solve time. One of the tricks that we're seeing here is a high aspect ratio cell. It's why this looks like a rectangle instead of a square. The square is sort of the default mesh. The long, thin rectangle is the high aspect ratio element. So as I'm trying to follow these best practices, 2-3 cells through each gap, we're seeing that mesh cell count increase by quite a bit. So on my computer, and on the best computer, that was over 2 hours to solve with just the 2 cells in the gap on the 6 million cell count. Trying to improve that, 3 cells in each gap, 4 cells in each gap, I'm only getting higher and higher cell counts and longer solve times. So I really would not want to do this when I'm trying to do fast iterations, but I would likely take advantage of this when I get into the more detailed final analysis, where I'm trying to look at the temperatures in the battery cells in a more final design. But I should also understand the inaccuracies that I brought into this by using these high aspect ratio cells. Those can bring in inaccuracies, and I should be aware of what that's doing. So let's take a look at high aspect ratio mesh. Can I come up with a pun? We're going to look at the highs and lows of aspect ratios. Okay. So I want to understand aspect ratios and how that's affecting my results. A cube is ideal. A square element, which we saw in the screenshot, which is a cube in a 3D model, that's an ideal. That's an aspect ratio of 1. As I skew that into rectangular prisms, my aspect ratio increases. This is the equation, longest side versus the shortest side. Okay, doing some very simple hand calculation versions of this. Imagine T1 is generating heat. When I'm looking at just conduction, majority of the conduction is going to transfer into the cell T3 because it shares more area with T1. Because T2 has reduced area now, it's going to have a lower amount of conduction passing into it. So that's the main way that I'm affecting my results adversely. My conduction is now happening more across the cells that share a larger area. Between T1 and T2, the heat transfer is largely going to be through convection. Okay, something I need to keep in mind as I look at my results later. How do I create high aspect ratio elements inside of SOLIDWORKS flow simulation? This is a mesh setting. These are called control planes. So I might pick the boundaries of where I want the cells to start squeezing together. Then I pick a size. So hey, instead of the default cube size, I want to do something a little bit thinner. That's what I'm setting here, 0.001. Now the ratio that I'm doing around this, you can see that extends the cells kind of before and after those planes and tries to stretch them back into a cube shape. So it's increasing the ratio between the thin cell to the large cell. Okay, let's do this in a very extreme way. When I did the initial default mesh with the cubes, that was about 615,000 cells. I did a very extreme high aspect ratio cell. This was half the amount of cells that I had before, solved faster. This is going to show us the goods and bads, the highs and lows of high aspect ratio cells. All right, so extremely large high aspect ratios. Let's take a look. So just looking at the max temperatures in the cells, this is not too far off, surprisingly. Pretty similar. Also, the general distribution, fairly similar. But if I take a look at the cells on the far end, I'm seeing a temperature variation there. So that's not matching for some reason. Look at this slightly differently. This is the heat transfer coefficient. Remember, that was the H in the equation we looked at earlier. With those extremely long high aspect ratio cells, so those are long in the direction I'm moving my mouse right now, axially along the fins, but they were also long in the vertical direction. This is pretty clearly erroneous. This is really skewing the way the heat transfer coefficient is being applied to these fins when I made those very long. Pressure and velocity. My pressure drop across the fins almost doubled with the higher aspect ratio cells. And if I take a look at the velocity gradient just around that inlet area, with the default mesh that smoothens out and transfers left and right a little bit easier, that's not happening with those high aspect ratio cells. Okay, so what did I learn? Yeah, it can improve solve time. It can help me follow best practices by getting more cells across the channel, but I need to watch out for those heat transfer coefficients and how I'm skewing them. I definitely need to watch for velocity and pressure gradients being affected by creating these higher aspect ratio elements. It does affect the way the velocity is transferring across them. It does affect the way the pressure's moving across them. So I need to watch out for those changes as I increase the aspect ratio of my cells. Now, I understand that it's not possible to completely ignore them. In the best practice mesh I was looking at earlier in the slide deck, I had used those high aspect ratio elements, right? I just didn't have them as extreme as I ran in this sample. But as I was bumping up the high aspect ratio cells, going from 2 fluid cells, 2 partial cells, to 3 fluid, to 4 fluid, I should be watching those velocity and pressure gradients and make sure they're not worsening, make sure I'm not affecting them as I'm increasing that aspect ratio. Okay. That was fun. I know there are other ways to build structured meshes outside of what I just showed from SOLIDWORKS FlowSim. These are possible in the 3D Experience platform. I'm going to take some time to investigate this further a little bit later. But for now, let's take a look at porous media. All right. If you pour some time into porous media early in, you can save a lot of time later. All right, what is porous media? The idea is using a porous media block, like a three-dimensional prism, a rectangular prism, to replace a dense bank of CAD data. In this case, many of the fins. There are some things I'd want to think about before generating a porous media block. For example, should I run this for just a few fins? Like this is 4 fins. Should I run it for 6, 8, 15? The more fins you run this on, the better average you're going to get for what is happening with that pressure drop across these fins. So the more you run, the better your average result. Something else I want to look at, where do I put my inlet and outlet? The inlet in this case is sort of purplish block in the front end of these fins, and the green block is the back end, the outlet. So what I would recommend, put that inlet and outlet a little bit away from the fins so that you have a lead-in of air. So don't put them right on it like this. Have that inlet be a little bit further away, like this. Then you have a lead-in of air into the fins, and you create a better curve after the fact. Let me show you a little more what that means. So in flow simulation and 3D experience, there are methods of doing a batch run. What I would do is at the inlet have a varying velocity. So vary velocity from the lowest possible velocity that might be hitting those fins to the max possible velocity, and be measuring pressure drop from inlet to outlet. So across that bank of fins, I would create a curve something like this. So as velocity fluctuates, pressure drop fluctuates. Great. I replicate this for the heat transfer. It's a little bit different, but similar process. Take a look at this bottom left picture here. I've blocked off fins that are around other rows of battery cells. I'm just focusing on one row of battery cells and the fins that span that area. And then I would do the same idea. I would have an inlet and outlet. I would subject it to a range of velocities. And then I would output the heat transfer coefficient over this volume. Let me talk through the equation I have here at the top of the slide. So I would get a sum of all the heat transfer coefficients on every single fin. So I'm selecting every face of the fins, of all the fins, and adding together the heat transfer coefficient. I do the same thing for the area. What's the total area of all of these fins? Multiply that together. For the volume, if I was going to create a rectangular prism that perfectly encapsulated all of those fins, what would the volume of that prism be? That becomes V1. Plug that into the equation, I get the volumetric heat transfer value. Do that for every single velocity, you get a curve like I have here in the bottom right. That's the volumetric heat exchange value. Then we plug this into the tool sets. SOLIDWORKS flow simulation, 3D experience sort of works the same way. I take my fins, I replace them with a block. This is flow simulation, but this is going to a porous media block area. And I put in my tables. So pressure drop versus velocity for the first set of data I had generated, and the volumetric heat exchange coefficient versus velocity for the second set of data. Even though I did that for only one column of cells, or one row of cells there, the porous media tools in CFD programs can extrapolate from just that one cell and apply it to the whole volume. So it can extrapolate. That's a great time-saving technique. Let's take a look at some of the outputs here. So this is replacing the fins with that porous media block with data generated just based off of one column and then extrapolated out. Fairly similar results to what we were getting with the default mesh. Now, what I'm comparing here is isotropic versus unidirectional. Let's talk about what that means. Isotropic is looking at the X, Y, Z, all three directions that the fluid could move once entering that rectangular prism, once entering that porous media block. Isotropic means it can move in all directions, and it's having its pressure drops and heat exchanges in whatever direction the fluid is moving. Unidirectional, when the fluid hits that block, it's forced to follow a particular direction. So in the example of one of these porous media blocks, I could say the fluid is entering through here and then forced to follow sort of axially along the fins. It's forced to move in the X direction, let's say. It cannot move in the Y direction vertically. It cannot move in the Z direction crossing fins. So there's goods and bads to that. Forcing it to move along the X direction is pretty much what the fluid is doing in reality. However, in reality, it's also able to heat up and rise because heat rises. And if I use unidirectional, I'm not factoring that in. So understanding our assumptions, right? So when I used unidirectional for this porous media block, I did keep the fluid from crossing left to right in the way the fins would prevent it from moving, but I did prevent it from rising, so I did have some effect on the temperature. But in general, fairly similar. Porous media, definitely a way I'd want to take advantage of as I'm comparing inlet and outlets and trying to improve those designs. Can make the solve times extremely efficient. But getting into 3D experience and other types of structured meshing, other types of solving capabilities available to me, cloud computing. I'm going to start with partition hex mesh and this idea of the structured meshes. The 3D experience platform doesn't require that I use this meshing method. I could use what methods I was doing formally in the presentation. But this is just an intriguing option that I can take advantage of here. So instead of using the automated meshing tools, like the control planes, the high aspect ratio elements, some of the automated meshing tools that I have, this is going to be very manual mesh creation. A lot more work on the front end to make happen. But I gain a lot of control over mesh creation. So I can create a mesh that accurately represents what's going on around these fins, but ideally create that mesh that's still very efficient to solve. To follow this idea, I would need to create physical geometry, physical CAD geometry, to represent the fluid region. Fortunately, in SOLIDWORKS, this is not too hard to do. Really just a couple clicks. This is called the cavity command. I would take a block, I use a cavity, I basically subtract out my heatsink geometry from that volume. And so I end up creating a block that is representing the fluid. It's called the cavity command. In the platform, I partition the volumes. So I'm essentially saying, hey, at the boundaries of these fins, I want to split off the inlets and outlets so that I can have different types of elements over there. So I can do that on both sides, just generating separate partitions, separate volumes. Once I have those separate volumes, I can create different mesh cells, mesh sizes for those volumes. So in this case, I'm making the mesh cells on the tops and bottoms differently. And then along the kind of channels between each fin, I'm making the mesh cells smaller. Notice so far I've only been using the perfect square elements to do this, right? But I'm still following those best practices of multiple cells across the channel. But let's talk high aspect ratio or aspect ratio in general, because you can take advantage of this on the platform. I'd use something called edge distribution to do it. In this case, I'm saying, hey, along this edge, one of the channels between the fins, I want multiple cells. I want to grow those from thin to thick, increasing that ratio. I'm creating a mesh that looks a little bit like this. So you see that variation, thinner along the walls, thicker along the center, but I'm creating a lot of mesh cells. This idea of a growth ratio, it's in FEA, it's in CFD. The idea generally is the slower that you have that growth ratio, up here is faster, down here is slower. The slower I do that growth ratio, the more precise my results, the less error I'm introducing into the analysis. So a slow, steady growth is typically better. Now, the kind of final mesh that ends up here in this sample, I didn't use this for the full 250 fin model that I was generating. I'm just showing this as a sample here, but want to show you how that would be done. This is more what I did as a first pass. There's some goods and bads to this. The good things, hey, I've got a couple cells across the channel. They're not skewed at all. They have perfectly cubed shapes. Some of the downsides to this mesh, I didn't use any growth ratio between the large and small cells. That's not a good idea. I should have had that have a steady transition between those two styles. But this is a proof of concept. What did that generate? About 23 million cells. To solve locally, that took about 8 hours on my machine. Fortunately, if I'm using the 3D Experience platform, I do have access to cloud computing. Out of the box, I have access to up to 16 cores. That's already better than my local computer, 8 and 16. And this is free. I could use it as much as I want. The higher CPU counts are only available with some prepaid methods. If you think back to the comparison we did at the very beginning of this presentation, where I was comparing between my computer, my coworkers, and one of our better computers that we use for simulation services, I was increasing the CPU count. I went from 6 CPUs to 8 to 24. And as I went up, that improved the solve time. So that's the idea here. For something like this, which is just a ton of mesh cells requiring a ton of RAM, increasing the CPU count can also improve that solve time. All right, let's take a look at the results from the structured mesh approach. Higher temperatures in general, similar distributions. I'm likely getting closer towards a more precise result here. Looking at the velocity gradients, this is very similar to what I was seeing with the default mesh. You kind of see that here. The turquoises are quite similar. But I do want to point out this sort of very subtle deviation there along that solid black horizontal line. That's where my mesh changed in size, where it went from the large cell to the small cell. So that's more proof of when your gradients between your cells are not good enough. Like your growth ratio should be improved when you start to see these deviations. That's not good. Let's see. Let's move on to kind of summarizing everything that I talked about. So basic mesh and high aspect ratio meshes. The basic mesh was not a bad idea. It was solving fairly efficiently. It was generally close to the final detailed results. It was pretty good for initial design iterations. So I would take advantage of that basic mesh for looking at improving my velocity distributions on the inlet and outlets, my general pressure drops. It would be helpful for that. The high aspect ratio elements, I have to be very careful when I start taking advantage of them because they can be inaccurate. So if that was my only method of looking at this, I would want to make sure I just use this approach to get an idea of what the answers are going to be, and then I need to compare against physical testing later. I will have to do empirical testing. So again, early design iterations, use it for comparison, but it's not the end-all be-all of my results. For porous media, I have to take the time up front to build pressure, velocity, and heat exchange datasets. Just keep in mind that those datasets that I generated were for a very particular size and shape of fins. If I was going to change the height of the fins, the width of the fins, the density of those fins, pack them closer together or further apart, I would have to regenerate that porous media data. Just keep that in mind. But again, the benefit, you can do that for just a couple cells, just a couple fins, and then you can extrapolate that to the larger system. Finally, something like a structured mesh approach possible in 3D Experience platform or other CFD tools, really detailed control over what you're doing with your mesh, what the growth ratios look like, where your aspect ratios are versus not. And you have access to cloud computing, very helpful for these sort of massive cell counts, or potentially even if the basic mesh on this sample model, if that was even too big to solve locally in a far more massive heat exchanger, at least I have cloud computing to solve it, right? So useful for final detailed design or super large heat exchangers. All right, that's my summary. I have some other things I could talk about as part of Q&A, but first I'm going to take a look at what's been going on in the chat. Why did I talk about best practice meshing being 2 to 3 cells between each channel? Like, where is this all coming from? So when I talk about efficiency or optimizing, things like that, it's because we're not working with AI yet, which can predict what we want to do. We don't work with supercomputers that can predict the CFD and solve it instantly. We're trying to find things that can solve efficiently, right? But the idea of the 2-3 cells across a channel, where am I coming from that? Where is that coming from? It's building off of this idea of a mesh sensitivity study. This is the idea that you start with a coarse mesh and you get some set of data. And then you make the mesh a little bit smaller and you compare your results. And you do that over and over until your results stop changing. It's a converged solution. The mesh is no longer affecting my results. When you do this for a lot of different types of studies, or if you do this for the heat exchanger, for example, if I just focused on making them smaller in the heat exchanger, I would likely notice after about 2-3 cells between each fin, I'm not seeing much change in the pressure drops and the velocity gradients. It's fairly uniform at that point, or fairly converged at that point. So that's where 2 to 3 cells is coming from. It's this idea of a mesh sensitivity study. High aspect ratio elements. They can add inaccuracies to the study. They are unfortunately a necessary evil for solve time efficiency. So just keep in mind what they affect so you don't create too crazy of an aspect ratio and have a adverse problem. They are actually very commonly used in other areas of CFD. I had briefly mentioned the idea of airfoils at the very beginning of the presentation. So high aspect ratio elements are used, or when we're predicting lift and drag around an airfoil. We use it around the trailing edge of an airfoil. Some of that idea is built around this idea of a boundary layer. This picture here, I pulled it off of Wikipedia, but this is a boundary layer where the idea is the velocity in a free stream flow up here at the top is lowering down to about 0 or exactly 0 at the wall. And there's a sort of profile and how that grows from the wall to the free stream. There's a similar idea for temperature gradients. There's a thermal gradient boundary layer near the wall. These can be different sizes. The size of them depends on fluid viscosity, velocity, laminar and turbulence, etc. For the system we were looking at here, with water flowing over heat sinks, with water flowing over the wall, it would look fairly similar to what we see here. The thermal gradient would be a little bit smaller than the velocity gradient. Now, if I zoomed in very close to the wall, the boundary layer would look a little bit like this. So this is not a perfect, pretty little parabola. It's a funky shape. And it's made up of multiple segments. I've got this viscous sublayer, the buffer layer, and the log-law region. The viscous sublayer and the log-law region, we have some good methods of mathematically approximating those things. We don't have very good methods of approximating the buffer layer. Simplify the graph for a second. I want you to imagine mesh elements about this size, so larger. A larger element that's way outside of the viscous sublayer in the buffer region, it starts at least in the log-law region, or the outer layer, the free stream region. Every single mesh that I did in this presentation were these types of mesh elements. They were far outside of the thermal gradient. They're far outside of the boundary layer. When we use cells that are that large, CFD programs will typically do a mathematical approach to what is happening in that boundary layer. It's called a wall function. CFDs will have multiple styles of wall functions, multiple types. So it's just using an approximation of what's happening there. Now you can go as far as creating cells that are smaller than that buffer layer. So starting in the viscous sublayer, you stack them up. At that point, you're calculating literally what's happening in that buffer layer. You're adding that little bit of extra precision to the velocity gradient that you're calculating, or the thermal gradient that you're calculating. You would never do that with a perfect square cell. It would be extremely long to solve. So that's another area where high aspect ratio elements are coming into play.